How are you guys? Good morning, Johnny. Yes, Papa. Okay. Eating sugar, Johnny, today? No. Ha ha ha. Okay. All right. I believe you are quite busy with your test one, right? So many of you are busy right now with your test one. I'm also busy with marking your test one. Right. Okay. I will not comment on that. Um, by the way, we have two topics need to be covered, right? Because next week is Hari Raya, I think. Okay, maybe, right? Hari Raya, right? Okay. Next week is 1 May, right? Okay. It's holiday. All right. Are you ready, guys? Without further ado, so let's me start our class for today for the new topic, which is filter, and the next one will be Western Bridge. Okay. All right. Ready? Tutak, 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 tutak. Zah. Fire. Okay. All right. Everything good. Same rabbit. Okay, good. So filter. So let's me recap back on what you have learned before. Okay. All right. So when we talk about the instrumentation system, that means there are 4 components that involved in the instrumentation system, which is the transducer, and then you have the signal conditioning, and also you will have the analog to digital, and then you will have the display. Okay, so this one is the transducer, and this one is signal conditioning, and analog to digital, and also display. Okay, so on what we have learned before, we know that transducer, we convert it into useful value. For example, it detect the temperature, it can convert it to a very small voltage, which is a millivolt, and then we use the signal conditioning, whether to amplify, whether to attenuate, whether to uh, convert to others parameter, right? Like ohm, it can convert into ohm also. It can amplify, right, to voltage. And also the signal conditioning also can be used as a filter. Okay, on what we have learned for today, right? So how the filter it works is like, for example, if you have at this point, right? If you have uh, your signal, right? For example, right now in term of t, okay, in term of time, and this will be your what we call it the signal in term of millivolt. Okay, this is your signal. So your signal have a ripple a little bit, or we call it a ripple. It's not we're not going to get a very straight line, right? And it will have some ripple a little bit, and your signal sometimes will have some noise. Okay, the green one is a noise. Okay, so when you enter to the filter circuit actually, so what will be happen is it will it can amplify also, and it will filter out the noise, right? It will eliminate the noise. So maybe at that time it will become like, okay, there's no noise, right? So the ripple right now is a very small ripple, like the noise. Okay, so this is what we're going to learn in this topic. Right, guys? Okay. So if you look into that, this data, for example, is 5 volt. So when you put it into the filter, it will be a little bit lost in terms of the data. For example, it equal to 4 volt. Okay. We will look why the loss is happened. Okay, all right. Filter is used to filter out the unwanted frequency. So we call it is noise. Okay, from a measurement signal. Okay. Uh, for example, a transducer may convert temperature to DC voltage because of the present AC, that's mean alternate current. Okay, DC that mean direct current. Because of the presence of the AC power line, however, there will be 60 hertz noise voltage impressed on the output that we call the noise. Okay, so uh, in this case, for example, this is your output, right? So maybe at that time your cable is near with the AC cable, right? So sometime your application or your plant maybe need some the AC voltage. So it will create the noise. Okay. So the noise right now it will affect your data actually. Alright. So filter can be divided into passive and active. When I talk about passive, that means you don't need any power supply, alright, any what we call it, the external voltage and so on. When I talk about the active, that means something that you need a supply, right? Okay. Like I said, Amirul, so what are you doing? Okay, that means you will become active. Okay. Passive, that means it's like the passive component that consists of a resistor and capacitor, right? Resistor, you don't need a supply. Capacitor also, you don't need a supply. Active, that means a combination between amplifier and passive component. Okay, that is about. Okay, so when any circuit, for example, the filter circuit, right, that have the resistor and capacitor, that the the input voltage that consists of the AC, right, that enter to this filter. So right now, each component for R and C, it will react as the reactant. Okay, this is in terms of the theoretical, right? We react a reactant which is R will become ZR, so C will become ZC. Okay, right? So it doesn't matter this one. All right. So let's look the concept of the signal, or we call it your data, right? Data and concept of the noise. Okay. If you look at this one, when you have the signal from the transducer, we call this one. Okay. So for example, the output is 10 volt. Okay, the output is 10 volt here. Okay, and then your signal also have the frequency, right? So for example, the 5 kilohertz, and then at the same time, your signal also come with the noise, right? For example, the noise, the level is 5 volt. Okay, the peak one, the 5 volt, and then it also have their own frequency, which is 500k, right? 500k. So now when your signal with the noise, okay, so the output, right, the signal will be like this, signal with noise. Okay, understand? Right. So now for this signal, we need to decide so which filter that we're going to use, right? Which filter that we're going to use. So of course, we're going to filter out the noise, right? Okay. So for example, right now, when the filter, when we use the low pass filter, for example, it's combination between R and C, right? For the ideal, right? The V out from here will be equal to V in here for the ideal cases, right? For the ideal cases, that means there is no data loss and so on. All is perfect, right? R value is perfect. There is no tolerance value and so on. You will got it V out is equal to V in terms of the signal. 10 volt, the signal is 10 volt. Now the output is 9.9 volt. Okay, it's perfect, right? However, in practically, right? So this one 10 volt. So now you can get it 10 volt is perfect. However, in practically, right? When your input is 10 volt, when you enter to the low pass filter, you will got it is 9.9 volt in practically. Okay, so you will lose a little bit. You will lose the data, right? From 10 volt, you will lose to about 0.1. Okay, right? So this show that when the signal that enter to the low pass filter or any filter, you will lose a data a little bit. Okay, all right. And how about the noise? Okay, how about the noise? Okay, let's look at this. Okay, so for example, your noise is 5 volt, right? And then it will enter to the filter, right? So of course, we want to reduce the noise as small as possible. Oh, okay, good. Record the class. All right. Everything need to be recorded, right? Okay. All right. So now, when you want to reduce the noise, of course, you want to reduce, for example, from 5 volt, it become very small value, right? To 0.1 volt. Okay. So, or you want to reduce from the 100%, right? We can say that the initial one is 100%. You want to reduce to 2%. How did I know 2%? Right? So 0.1, my target value is I want to reduce to 0.1 volt. I divided to 5 volt, I time with 100%. Okay, now I will got it this guy. Okay, so that means I want to reduce noise to be 2%, right? That means reduce the noise to 2%. So from the 100%, you reduce 2%. Or some other words is attenuate the noise to 2%. Okay? All right. So how to do that? How to reduce the noise 2%? By choosing the value for R and also C. Right? This is for the low pass filter. Low pass filter. We will look what is meant by low pass filter. Right? So you need to choose the value for R and C in order to reduce the noise to 2%. Okay? Alright. So you know what I mean, guys? Is it clear? Clear to you, right? Yoo-hoo. Guys? Okay? What the percentage is it? What the percentage is it? Okay. How do you know the noise level? Okay. So the noise level you can decide. So that means 2% or 1% you can decide. Okay, you can decide. All right. So in this case, I decided, okay, I want my noise from the 100%, which is the initial one. In terms of the voltage, maybe our noise equal to 5 volt. So I want to reduce to be 2%. All right. So I can decide. All right. So when you set it at 2%, that means you need to choose the value for R and C, and then this R and C also will affect your signal. We will look into that. Okay, is it clear, Najmul? All right. So like I said before, when there is a presence of AC to the circuit, right, the signal, the resistor and capacitor will react as reactant. Okay, so we will consider this value before. So if we look into this, without the present AC voltage, so the equation will be like this. Is only the voltage divider R2 divided with R1 plus R2 you time with the Vin. Okay, this is without the presence of alternate current. So right now, how about the alternate current just go to this circuit? So you will look at the circuit right now. The equation will be ZC, right? Uh, Capacitance, right? So over with ZR plus ZC. So in this case, ZR is equal to R, and also the ZC will equal to 1 over CS. Okay. So what is this S? So ZC is depending on the d over dt. When you Laplace it, d over dt. So right now you got it S. So this one, it doesn't matter, is if you don't understand a little bit, it doesn't matter, this one. And omega c, so right now you will have it, you also can have it in the frequency fc, where the omega is equal to 2 pi r. Okay, so this is for your information. All right. Now let's look the type of the filter. Okay, so in this case, if you look at this one, so what actually we filter out? What actually we filter out, right? So that, like I mentioned before, we need to choose the value R and C. So the R and C, is it depending on the value of this one? So the peak value, R and C, right? Is it the R and C we choose here is depending on this one? No, right? The answer is no. R and C is only depending on the word that we call it is the frequency. What we filter out actually, we filter out the frequency. Okay, all right, let's look. All right, so there is three filter. One is the low pass filter. Then second one is the high pass filter. And the third one is the band pass filter. Okay, so what is do is, right, for the low pass filter, LPF, so it will pass, the frequency is from 0 to critical frequency. That means the critical frequency we can set it, right? Okay, from 0 to critical frequency, it will allow, right? It will allow. Okay, I put it like this, it will allow. Okay, so after the critical frequency, it will block. There is no output will be after that. Okay, so this is by taking V out over V in. Okay, the ratio, so you can get this graph, because the for V out over V in, right, that's mean so the output over the input. Okay, for the high pass frequency, from 0 to critical frequency, it will block, and then after that it will pass, right? It will allow, right, the output. Okay, right. For the band pass filter, from 0 to this critical frequency, we call it low critical frequency, it will block, and this one also will block, and in between it will pass. Okay, all right. So if I can draw it, it will be like this one. So this is the frequency, right? Whether it's frequency from signal or frequency from the noise. So the frequency will be allowed if in between this one. Okay, right? So this one, the frequency is FC. and this one the frequency is less than FC. Okay, we will look into that. All right, there are three types of filter. Okay, so how about okay, so let's look one simple one, right? Okay, that to make you understand a little bit. All right, so if you have a signal, right, your signal or your data that have the frequency about 500 hertz, okay, and then your noise that have the frequency of 400 hertz. Okay, all right. So you need to decide whether you want to use the LPF, low pass filter, or high pass filter. Which one, guys? Which one that you going to use? Low pass or high pass filter? What do you think? I give you some clue. Low pass filter. Yeah, Najmul said low pass. Johnny also said low pass. Okay, good. We look into that. Okay. This is your frequency, right? So the 400 is at here, 400 hertz. So this one you need the hertz. And then the 500 is here. All right. So now if you make it the high pass filter, right? The high pass filter, that means high pass or low pass, guys. High pass or low pass. Okay. If you make it the, let's say we choose the low pass filter. Low pass filter, that means choose here and here. Okay. Is it the low pass? Low pass, right? Yeah, the graph will be like this. Okay. So what it means if you use the low pass, that means let's say you choose your critical frequency here, FC. Low pass, the concept is below the critical frequency, it will pass. That means you will allow the noise go through, isn't it? Okay. So the purpose that we use the filter, that means we want to eliminate the noise. So that means if you use the low pass filter, that means you will allow the noise go through, right? See like this? Can you understand it? Okay. So that's why you need to use what? You need to use high pass filter. I'm right, guys? High pass filter. So that means it will, okay, all right. So this is, you can set it critical frequency. Okay, that means this one it will pass and this one it will block. Okay, can you understand it? So the answer will be the high pass filter. All right, get it? Understand? Okay, good. Okay, so this is the example. So we will look into the signal first. Okay, so where is your signal located, right? If your signal located is more than the noise, so that means you need to use the high pass filter. Okay, if your signal is located at this at on the left, so you need to use the low pass filter. So this one, your signal more than noise, So you can decide to use high pass filter. If the signal less than noise, you can decide to use the low pass filter. Right? That is the concept. Okay. Any question, guys? The concept is you filter out the frequency. It's not you filter out the amplitude, right? The peak level. Okay. The frequency response. So normally we plot it into plot, right? Okay, the bot plot. Okay. So we will plot it between the ratio V out over V in. Okay, normally, right? And then if you look at that, there is a critical frequency. This is where you set it. You can set by yourself, right? And also from the critical frequency, you can choose the value for R and value for C. You can set it, right? For example, for this one, I can set it, okay, I want the critical frequency equal to 450, right? And then from 450, I can choose for value for R and C. You can choose it. We will look into that. Okay, so let's go for the low pass filter. Okay, so the circuit for the low pass filter is quite simple. A combination between R and C. If you look at this value, the V out, you are taken from the capacitance, right? For the low pass filter. Okay, so what is does it too is that mean for the low pass filter the graph will be like this. Okay, so this one it will pass, right? It will pass, this one it will block, right? So this is one, it will pass, and this one will block. And then the calculation, right? The final one that you will got it is like this one. V out over V in here is equal to 1 over square root 1 plus F over FC squared. Okay, where your FC is the critical frequency, the formula will be always 2 pi RC. Right? So how to get this formula? So it is from V out when the circuit have become reactant, so it will be like this. V in. So where your ZC from previous formula, we know that 2 pi FC. Okay, that's why you got it V out equal to 1 over J2 pi FC divided with R plus 1 over 2 pi FC times with V in. Okay. So because of the FC equal to V out over V in, V out over V in, 1 over 2 pi RC. So when you multiply this one, okay, and so on, and finally you will got it this formula. Okay, all right. When you multiply and then you arrange back this one to here, right, and you will got that formula. I hope that it will be clear for you. Okay, all right. Okay, done. So instead of you measure in terms of frequency, you also can measure in terms of the omega, right? Radian. So normally we measure the frequency. Okay. So this is the what we call it, the graph for the low pass filter. All right. Then the detailed definition about low pass filter is given to you. So critical frequency, the equation is never changed, 1 over 2 pi RC. And then the what we call it, the formula for the low pass filter will be this one. Okay, so this is not the unwanted noise. So this is can become the signal and also the noise. We look into that. Okay, because the noise also will have the V in, right, the amplitude. Okay, the signal also will have the V in, the amplitude, and it also will have the output V out. Okay, so in order to choose the value of the resistor and also capacitor, so you need to choose, there is some rules, right? So resistor, you need to choose the value between 1K to 1 mega ohm. And for the capacitor, for value 1 micro to 1 picofarad. So this is used to for loading effect. So loading effect, that means the output from the sensor is a very, very small value, very, very small current and so on. So if you use the value for R and C is a very low, so it will lose the signal from that sensor itself. Okay. All right. So let's look example 6.1. Okay, 6.1. All right. Measurement signal. Okay. Now you have a measurement signal. Okay, signal, right? So you have the signal. Let's do this. Okay, so we have the word, okay, the signal, okay, has the frequency 1 kilohertz. Okay, we know that the frequency for signal is 1 kilohertz, but there is unwanted noise. Okay, now we have noise at the frequency 1 megahertz. Okay, so design low pass filter that attenuate the noise to 1%, reduce the noise to 1%. Right? And based on your design, what is the effect of the measurement signal at the maximum of 1 kilohertz? Okay, all right, guys. So if the question is never said design low pass filter, so how did you know whether you want to use the low pass filter or high pass filter? How did you know? Yes, you need to check whether your signal is greater or less, right? So in this case, your signal is less. That means you need to allow the frequency that less and the critical frequency first. That means you will use the low pass filter. If we look into this, okay, we have this graph. So now your signal is at 1K here, and then your noise is 1 mega. Okay, so the graph will be, okay, I allow 1K first, and then after that I will block. The graph will be like this. So that means your critical frequency, which is in between FC here. So what is this? Is the low pass filter. Okay, that is the concept, right? So let me delete this one. Okay, all right. So when the question is ask you about design a low pass filter, so it's a simple thing. So low pass filter, that means the output will be at the capacitor. So this the output, right? So this is the V in. The V in can be signal or can be noise. There will be two, right? Okay. So this is the R. Oh, sorry. So this will be the R, will be the C, and also will be the R. So our purpose is we want to find the value for R and C. Okay, so how to find the value for R and C? Right, it depending on your FC, because FC 1 over 2 pi RC. Right, so how I'm going to get FC? So FC is not the KFC, right? So FC you can get it from here, V out, right? V out over V in equal to 1 over square root 1 plus F over FC squared. So you can get the FC from here, right? Okay, you can get FC from here. Okay. All right. So how about V out and V in? Okay. So the question said that reduce the noise to 1%. That means your V out over V in right now is equal to 1%. Can you understand? Or, or I can write like this one. V out over V in is 1 over percent. Yes, yes, correct. Our V in from the 100%, so we want to reduce to V out is equal to 1%. Can you get it? So our V in 100%, the noise, okay, we are talking about the noise, we want to reduce it to 1%. Okay, good, Johnny. You good, all right. Although that you know, you not yet eat sugar, okay, good. Okay, so now is equal to 1%. 1%, okay, 1 over 100. So now 1 over square root 1 plus, okay, so 1% is belong to the noise, right? So we need to choose the F right now is the frequency of the noise. Right now is 1 mega over FC squared. Okay, so now 0.01 is equal to 1 over square root 1 plus 1 mega over FC squared. Okay, so let's me continue a little bit. So now we have the square root 1 plus 1 mega over FC squared equal to 1 over 0.01. And then 1 plus 1 mega over FC squared 0.01. And then you solve it, you got it your FC. So in this case, what is it, guys? You got it FC. I think 10 kilohertz. Good, John. Very fast, good. So 10 kilohertz, right? Okay, the Johnny got it, this one, good. Right, done. Okay, so now let's continue. All right, so from the critical frequency, as I mentioned before, you can determine the value for R and C. Okay, so FC, you got it, is 10 kilohertz. Okay, good. So 1 over 2 pi RC, you got it 10 kilohertz. Okay, so now we need to choose the value for R and C, right? That you need to follow the rules. So let's choose the value for C first. So in this case, I can choose the value for C like, yep, 0.01 microfarad. Okay, all right. So now how about the R? The R will be, depend on the ratio calculated. Okay. So in this case, I got it 1591 ohm or equal to 1.5 kilo ohm. Okay, so that means I have fulfilled, okay, the rules, okay, 1K and micro. Okay, done. Right. So you will see that your circuit now for the low pass filter. So now this is the V in, this is the R that you choose is 1.5K, and for the C value choose is 0.01 microfarad. Then you will got it your V out here. So from the noise, so I mentioned the noise from the 100%, we choose this value, you can reduce it to 1%. Okay, by choosing this value, R equal to 1.5K, C equal to 0.01 microfarad, you can reduce your noise to be 1%. All right. Okay, you can reduce the noise to be 1%. This is how you play around. Actually, you can set it. Okay, I want to set the critical frequency is 10K, right? 10K. That means this one you set it is 10K. So you will get it, the V out. After this, you will get the V out is equal to 1%. Or the ratio will be 1/100. Right? Okay, for the noise. Okay, so that means 100% it can reduce to 1%. Right? Good. Any question regarding this? Any question, guys? Is it clearly understand? Yes. Okay, good. Is it safe to always assume 0.01 microfarad? It is depending on your calculation. All right. So in test or in test, so we can accept if you don't follow the rules, we can accept that. Okay. But in practically, when you want to build a filter circuit, so you need to choose the value uh, for example, capacitor from micro to pico and resistor from kilo ohm to mega ohm. Okay. All right, Johnny. Understand. Good. Okay. And there is some part of the question as what is the effect of the measurement for the signal at the 1 kilohertz. Okay. Before this, we only look at about the noise. So the signal frequency here, it said that 1 kilohertz. What the effect? That means you still use the same value of R and C. What effect of your signal? That means the V out over V in. All right. Okay. So we will look into that. All right. So your V out over V in equal to 1 over square root 1 plus F over FC squared. So now is 1 square root 1 plus the frequency that you're going to choose is a signal, right? Signal. So 1K over with 10K here squared. So now you will got it here is about 0. What is it? Okay, 0.996, right? Okay, I'm right. Or it's about 99.6%. Okay, yeah. So that means your signal right now have reduced from 100% is reduced to 99.6%. That means you lost about 0.4% of your data. Okay, Oh, 0.995. Okay. All right. So in this case, you lost about 0.4% of your data. Okay. So if you can accept that, okay, I lost a little bit. Yeah, you can use this circle. Okay, you can use this value. You can use the frequency, critical frequency that you set it. Okay, this is how it works. All right. Okay. All right. So like I said, uh, for example, let's say we have the signal for amplitude of the signal is 10 volt, right? Now you can when you insert into the filter, now it will reduce to become 9.96 volt. Okay, this is in terms of the amplitude. All right, so this is the low pass filter. Okay, now let's look the high pass filter. High pass filter will be the same, right? Except we just switch it, right? Okay, this one goes to this, you want to do this. So if you look at this, so V out right now, we taken from the resistor. Okay, that is the high pass filter. Okay, so the formula will be same like low pass filter, except the low pass filter is 1 over, right? 1 plus F over Fc squared. Okay, this is the low pass filter. For the high pass filter, so you just delete this one and put it F over Fc and square. All right. So F refer here is depending whether signal or whether noise. Okay, there are two things, right? Signal or noise. Okay, right. Okay, this is the term of detailed explanation. The critical frequency will be the same, and then F that I referred here is the noise, or sorry, the signal. All right, signal and noise. Okay. All right. So we have know that when we use the low pass filter, there will be some of the data loss, right? So that's why they have created one filter. We call it low pass active filter. So low pass active filter is a combination between OM. If you can look at here, OM, it combined with the low pass filter. Okay, so what it called the low pass filter, you see the V out right now, it taken from the capacitor, right? So remember, the low pass filter circuit, the V out are taken from the capacitor. See, V out, V in, out. Okay, all right. So now the circuit will be from the inverting circuit, right? You see here, inverting circuit, right? And then you just added one capacitor here. Inverting circuit, added one capacitor here. Done. It will become the low pass active filter. So what is the formula? Formula is just a simple. So you from the low pass filter here, you just added again RF over R1. Okay, this is the formula for the low pass active filter. All right, you just added the gain RF over R1 here. RF over R1 is a gain, right? To amplify back the signal. Okay, right. Okay, let's do example 6.2. Okay, design low pass active filter. Low pass active filter, right? With cutoff frequency of 5 kilohertz and DC gain of 10. Okay, this is quite simple, very simple. So you have decided the critical frequency equal to 5 kilohertz, 5k hertz. All right, and DC gain, which is the word is G equal to 10. Design, when it's mean by design, that's mean you need to draw the circuit of the low pass active filter. So how to draw the circuit or low pass active filter? You need to design the inverting circuit first, right? Remember the inverting circuit like this, and then it have the feedback resistor and it have the input. Okay, so this one like RF R1. So this is the V in, right? V in. This is the V out. And to become a low pass active filter, you just added one capacitor here, which is C. Okay, and the formula for critical frequency will be the same, 1 over 2 pi RC, and the formula for the gain will be G RF over R1. Okay, done. All right, so when you set design, that means we need to find all this value, right? So RF and R1, you can find it from this gain. Okay, all right. In this case, for the critical frequency, R that's referred here is actually the RF. Okay, the R that couple with the capacitor. The R, the resistance that couple with the capacitor. That's why you taking the 2 pi RFC. All right, so let's do this one. Okay, so FC is given to you is 5k, so FC 1 over 2 pi RFC equal to 5,000. All right, and then you can calculate for the R, F, and C. You got it is about what is this? Okay, yeah, Johnny. All right, 3.183 times 10 power of minus 5. So let's say C, you choose it about 0.03 microfarad. So now you can get it, the RF is equal to, yeah, what is this? 1061. Okay, 1061 ohm. Okay, done. All right. And then from this one, you also can find RF over R1 equal to 10. So 1061 over R1 equal to 10. So R1 equal to 106.1 ohm. Okay, good. Thank you, Johnny. All right, this one. Okay, so we have calculate all these values for our low pass active filter. Okay, any question, guys? Any questions so far? Hopefully clear, right? All right, hopefully clear for you. Okay, all right, so before this we have the low pass active filter, then we also have the high pass active filter. Okay, so the difference is, remember, the V out we are taken from the output of R. So the difference between the low pass active filter, just location of C here, is from at the input. Okay, at the input. So that's mean for critical frequency also need to be coupled, right? For this one, the critical frequency here, FC is equal to 1 over 2 pi the couple of the capacitor, so R1 and C. Okay, all right. So the formula also will be the same. The formula will be the same, all right, except you just added the gain here. So in this case, if in terms of the frequency, V out over P in is equal to RF, the gain, R1, and you multiply with the F over FC squared. Oh, it's not squared, right? Not squared, okay. Square root 1 plus F over FC squared. All right, this is the formula. Like before I put the square or not? No, right? Oh, sorry, this one, right? Okay, good. Okay, all right. So it's from the high pass filter, and then it add the gain. Okay, all right. That's it. High pass filter, it add the gain. From this one also from the low pass filter, and then it add the gain. Okay, done. All right, so that's it for the high pass active filter. Okay, and the last one that we will talk about is the band pass. Sorry, this one is not band pass filter. So this one is the band pass active filter. Okay, so before we talk about the band pass active filter, so let's look about the band pass filter itself. Okay, all right. So I will make the new notes here. Okay. Now let's talk about the band pass filter. All right, band pass filter. Okay, so if you look at the graph for the band pass filter, it will be like this one. Yep, and then it will go down. So that means there is two critical frequency here. And what it does is this one, okay, it will pass. So this one it will block. All right, so for the critical frequency, like I said, this one is the F1 and this one is the F2. Okay, so what is the value for F1 and F2? Okay, so if you look at this graph, the first one will be high pass filter. Remember? High pass filter. And then after that, we go to the low pass filter. So that means your band pass filter is combination between high pass filter plus with the low pass filter. Okay? Right? If we divide it into these two graphs. Okay? High pass and also low pass filter. Alright, so let's draw the circuit. So that means combination between high pass, that means capacitor first, and then the output will be at the resistor. Okay, so let's say this one is C1, this one is R1, and this is the V in. Done, the high pass filter. And then if we go to the low pass filter, so low pass filter, it will output from the capacitor. Okay, so this is the C2, this is the R2, then this one is the VR. All right, okay, so the frequency, it will be two critical frequency, which is R1, 1 over 2 pi R1 C1, and the frequency number 2 is 1 over 2 pi R2C2. Okay, all right. So this one sometimes we call it the FCL, right? Critical frequency low, right? Yeah, that is low frequency, and then this one critical frequency high. Okay, that is the band pass filter. All right, can you understand it? Right. Okay. So let's say that we want to allow the frequency is from 10 hertz to 10 kilohertz. We want to allow, right? We just allow this frequency between 10 hertz to 10 kilohertz. So in this case, you can design the band pass filter, right? For F1 equal to 10, 1 over 2 pi R1C1, R1C1. So you can choose the value for R1, for example, is 10K. So C1, when you calculate it, so you got it 1.59 microfarad. Done. And for 10,000, so you also can calculate for value for R2 and C2. For example, R2 you choose 10K. Now for C2 you can choose 159 microfarad. Okay, this is how you design your band pass filter. Right. For example, you want to allow frequency 10 to 10,000. Okay. All right. How about the gain? The gain for the band pass filter. Okay, the gain will be only 1. Okay, the V out equal the V out divided with V in, right? The maximum that it can go for the gain is 1 for the ideal stage. Okay, all right. And the last one before we take a break. So the band pass active filter, yes, a combination between the high pass filter and low pass filter. If you look at this, it will be the high pass filter, it will be the low pass filter, and combination between the inverting, right? And then the calculation will be too long, right? And then you will got this formula lah, right? But normally we don't ask you about how to derive all this formula. Okay, we will ask you about the basic thing lah, right? The high pass and also the low pass. Okay, okay, and the FCL, it is, and depending, this one is what we call it the high pass filter, this one is the low pass filter. All right, so this is the example yeah, that I calculated before. Okay, 10 to 10,000, and if you have the active filter, you also can set the critical frequency, the same one. But the difference between the active and also passive is also the gain you can set it, right? The gain you can set it depending for the R2 and also R1. Okay, R2 and R1 you can set it again for 10. All right, so that is all about the filter, right? Any question, guys? We have go through low pass, high pass, low active filter, high pass active filter, and band pass filter and band pass active filter. Right? So back in your mind, we filter out the frequency, right? Only low pass filter lose some signal. Not really. High pass also you will lose some signal too. High pass also. But the example in this slide, so we don't have any example about the high pass filter. But try to look at the previous test. Will be a lot of the example on the filter for the high pass filter. Okay. We will take a break for 5 minutes. Then we will continue again, guys. Is it okay? Okay. All right. Good. All right, guys. So we continue. All right, I have sent you the previous test, right? It's about the filter. So if you can look into that, where is it? Okay, so uh, okay, question 2 for A, sketch a band pass filter, passive filter. Okay, this passive, right? So that's mean only uh, have the passive components. So this one I think you can design. You can sketch, right? So let's look the B. Sketch a low pass filter circuit that has that consists a supply voltage V in, V out, resistor 4.2 and capacitor 50 nanofarad. Calculate the V out for the input supply of 10 volt and also 10 hertz, right? 100 hertz. So in this one, we know that the low pass filter, it will be the output at the capacitor, right? Okay, so this is the V in. This RF is 4.2 K, and also for C equal to 54 nanofarad. Okay, this is the V out. And from this one, we are given also V in is 100 hertz. Okay, and we know the formula for the low pass filter is given to you V out over V in. Sorry, V out over V in is equal to 1 over square root 1 plus F over FC squared. Okay, so first of all, you need to find the FC, right? Okay, so FC equal to 1 over 2 pi RC. Okay, in this case, 1 over 2 pi R 4.2 K, and C is 54 nanofarad. All right, so you got it, the FC, right? Johnny, come on, calculate this one. And after you get your FC, now you can calculate it for V out over V in. So 1 over root 1 plus the F, that frequency right now is from the signal, right? 100. Divide the FC that you got it. Okay, to 701. Okay, good, thank you. Square. Right? And that one you will got it is V out over V in. Okay, what is this value? Ta-da! Come on, Johnny. Okay, 0.989. Okay, something like that. All right. So you want to find the V out. That's mean the V out. So 0.989. You need to time with the V in. So in this case, your V in right now is equal to 10 volt, right? 10 volt. That's mean 9.89 volt. Okay. All right. This is the example if you want to find what is the amplitude, right? What is the value of V out. So you can see that it have reduced a little bit the data, right? From 10 volt, it reduced to 9.89. Okay, right. That is the calculation. All right. So the next example also, it will show you what is state of the type of filter one. So what is this, guys? High pass, low pass. The output is from resistor. Okay, good. So this one, the high pass. Okay, so you can find the value for Rx, right? Actually, the Vx is over Vb in here is equal to F over Fc divided with square root 1 plus F over Fc squared. Right, so you can find the value for Vx here. Okay, we want to know the value for Vx because the F, the frequency that we got it from here is V in, we know. Okay, F equal to 10. Fc you can find it from here, so Fc equal to 1 over 2 pi, and then you time with 4k, and then you time with 795 pico. So you got it, your Fc done. Okay, so F and Fc you got it, so you can find the Vx here, which is this value you need to time with the V in. Here you get it, right? Get it, right? Okay, and then after that, this one, what is this, guys? The signal conditioning. You remember? Yes, it's inverting. What is that? Is a voltage follower, right? Voltage follower, right? So that's mean this Vy will be equal to Vx. Vy will be equal to Vx, right? Voltage follower. And then after that, the filter number 2, what is this? It will be low pass active filter. It had a gain, right? Okay, it had a gain which is Rf over R1, which is 5k divided with 1k. So the gain is 5. All right. So the last one that you want to find is V out here over V in equal to Rf over R1. And then this is low pass, that means 1 over square root 1 plus F over Fc squared. Okay, so it will be a little bit tricky. So Fc equal the couple of the capacitor, 1 over 2 pi 5k you time with 6366 pico, the couple, right, of the capacitor. Okay, and V out equal to all this value you need to time with the V in. So where is the V in is equal to V1. Okay, can you get it, guys? Can, right? I want the mark for this. Okay. All right, so try to do this one, and if you have any question you can ask me. All right, so let's move on. So today cover for 50% of test 2. Not yet. The test 2 will be I think will be this topic and also another topic. I can say yeah, almost 50% joining. Okay. All right, so next one, let's learn about the bridge circuit, right? Western bridge. Sometimes we call it the Western bridge, WP. I don't know why the Western. Why it's not something else? WB. Okay, so like I mentioned you before, Western bridge is also some kind of the signal conditioning. So when we have our transducer here, and then we have the signal conditioning here. So what it do is, for example, our temperature transducer detect temperature, it will produce in terms of ohm, right? This can be like the RTD or thermistor. Yep, it can produce in terms of ohm. And then when using the Western bridge, it can convert it into other parameter. It can convert it into the millivolt. Okay, so this is what you use the what we call it, the the Western bridge. So if you look at this, normally, for example, it detects 25 degree, okay, and it will produce 2000 ohm, right, 2 kilo ohm. And then when we use the Western bridge, we can convert it into 5 millivolt, for example, right? And then suddenly the temperature, it has increased for 1 degree. Okay, maybe at that time the ohm will be about 2001 ohm, right? 2001. Okay, so if you look at that, uh, the increment of the resistance itself is very small, right? Instead of, if you use the Western bridge, so maybe at that time you can get it is 10 millivolt, right? So the difference between this one is about 5 milli, right? 5 millivolt. So this one is about 1 ohm. 1 ohm is very, what we call it, very difficult if you want to get accurately, right? Because when you want to measure the ohm, is depending on the length of the wire, right? Is depending on the point that you put your sensor itself, right? Okay, for example, like I said, okay, this is the one wire, right? So I have a sensor that measure the ohm. So I put, this is the starting point, right? Starting point 0. I put the sensor here. So maybe at here, it will give you about 400 ohm. But when I put the sensor at here, right, it will give you the value is for 105 ohm, for example. So it will give you the different value because the resistance itself is depending on the length, right, of the wire and so on. So that's why from the ohm itself, we try to measure in terms of the voltage, right, or the current. Okay, maybe okay. Okay, so for the bridge circuit, you used to convert the impedance, which is the resistance variation, into the voltage variation. Okay, and is used to measure very low value of the resistance. Yeah, very low in terms of milliohm, right, and so on. And it also can increase the sensitivity of the impedance, right? And the most common or simplest one, we use the DC Western bridge. Okay, so DC Western bridge is shown is here. It have the supply, right? The Western bridge is the active components. So you have the supply, and also you have 4 resistors here. If you look at here, okay, and normally we can put your sensor here, and you will also have some of the variable resistor, right, to adjust so that you can get it the output from here, right, initially will be equal to 0. Okay, right. So let's derive the circuit, right? It will be like this. Okay, like I mentioned before, it have the supply, which is V in, and then it have the 4 resistors, R1, R2, R3, and also R4. Alright, so and then this one will have the D, right? The D, we call it the offset voltage, or sometimes we call it voltage detector, or sometimes we write it delta V. Okay, so normally we use the delta V equal to what? Equal to point A, VA minus the point B, VB here. If you organize your circuit, will be like this, right? So you can see that the VA is actually the voltage divider at the resistance value R3 divided with R1 plus R3, and then you multiply with the Bin minus with for VB is the voltage at the resistor R4, and R2 plus R4 you time with Bin. This is delta V. Alright, so and then you try to simplify it. So you got it R2 R3 plus with R3 R4, right? And then minus with R1 R4 minus with R3 R4 divided with R1 plus R3 time with R2 plus R4. So this one we can put it in here. All right. And then we look at that, you can cancel out this one. So now it can become for R2 R3 minus R1 R4 divided with R1 plus R3 time with R2 plus with R4. So this one delta V over Pn. Okay. So if the delta V equal to 0, at this point equal to 0, what it means is you will got it is delta V equal to 0. You will got it is R2, R2, R3, and R1 equal to R4. Okay. So what it means is it will cross, right? R1 time with R4 will be equal to value R2 time with R3. So that will make the delta V equal to 0. Okay, right? So when you want to do some measurement, right, you will try to set it the delta V equal to 0, right? How to set it is we can have a variable resistor to tune, right? To tune it to make a delta V equal to 0. Okay, that's used for Western Bridge. Right, so let's look at example 7.1. I believe this one will be very simple. Okay, if a Western Bridge null with R1 equal to 1000, R2 equal to 842, and R3 equal to 500, find the value for R4. Yeah, is quite what we call it, easier, right? Okay, so when it null, that's mean the cross one, so we can have the R2 equal to R3, R1 equal to R4. So we have 842 time with R3 500, R1 is 1000, and R4, and of course you can get the R4. Wow, Johnny, 421 ohm. Okay, thank you, Johnny. Right, so R4. Okay, the next one is the resistor in a bridge given by R1 equal to R2 equal to R3 equal to 120 ohm and R4 equal to 121 ohm. If the supply is 10 volt, find the voltage offset. Okay, so like I mentioned you before, so in order to draw the Western Bridge, it will be in terms of diagonal, this one. Okay, right. So the supply voltage is 10 volt. Okay, done. R1, so let's say R1, and then the cross will be R4. This one will be R2, the cross will be R3. So R1 is 120, R2 also 120, R3 120, and R4 121. So what will be the offset for this one is delta V. So the question is what will be the delta V, right? So delta V equal to VA minus VB. So the point as this one A, point this one is B. So VA, that's mean at the resistor R3 120, so 120 plus 120, so we can get it delta V over V in here, right? Okay, minus with VB, the point at the R4, so 120 plus 121. Okay, right. So then delta V over 10, what you got it here? And then ding 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 ding. Oh, come on, Johnny. Okay, minus 2.075 times 10 power of 3. Okay, so that's mean the delta P will be minus 20.75 millivolt. Okay, you can put it here. All right. Okay, good. So it doesn't matter if you got it is minus. It doesn't matter because the minus, that's mean because you use the formula VA, right? VA minus VB. Okay. So if you use the formula VB minus VA, you will got it positive value, right? For the Western bridge, it doesn't matter you got negative or positive. So the most important thing is the value. Okay, 20.75. All right. Okay. So what it means is like this one. So for the 1 ohm, it will increase about 20.75 millivolt. Right? For the 1 ohm. Okay. Right. You know what it means? Okay. Right. For example, if you set it 120 ohm, so right now you will got a 0 here, right? Because everything is same, right? This one cross equal to this one cross. And when the increasing for the R4 for 1 ohm, you will got it, the output will be from 0 volt to 20.75 millivolt. Okay, but of course you need to amplify a little bit. All right, 20.7 millivolt. Okay, so that's it. All right, so when you want to apply a sensor or transducer to the Western bridge, so the first of all you need to try to choose, right, the resistor value, right, for R1, R2, and R3, right, or R4 is equal to the initial value for the sensor itself. Okay, so like in this case, so let's say the value of the sensor is R, right? So we choose all the same value, R, and then because of the sensor itself, it will have the increment value, right? The changes value, we call it delta R. So the equation will be like this one, right? So you can put your sensor whether at this one or this one. It doesn't matter. Okay, right? Okay, so for example, you want to find what is the relationship between this one. So you can put the R plus delta R, right, over with R from here, R here, plus with R delta R here. Okay, right? It is like this one is like the R3, right? R3, right? R3. And then minus with R is like the R4 here, right? R4, R minus R divided with R plus R. And blah, blah, blah. You derive it and then you try to make it so you got this formula. Delta R over R, 4 plus 2 delta R over R. So sometimes we can simplify it again, right, to become only delta R over R divided with 4. Alright, because the delta R divided with R will be almost 0. We can ignore it, right? Okay, because you can say that 4 plus 2. So you can ignore this one, right? Okay, you can ignore this one because it's a very small value, right? So we can only take the 4. Okay, alright. Alright, so the last one but not least, let's think about this one. For the Western bridge shown below, show that the V out equal to 10 RT divided with 500 plus RT minus 5. Okay, so how to calculate this one? Okay, it's a simple thing. Like said, if you can get it, this is point A, this is point B, so you can calculate like this one. Okay, blah blah blah. So let's say this one is point A, this one is point B. So you can calculate VA minus VB. So VA is RT divided with 500 plus RT, you time with 10, which is V in, and minus with 500 divided with 500 plus 500, and blah blah blah, and then you can solve with this one. Simple. Okay. Alright. And show the sensitivity of V out with respect to RT equal to 5 millivolt per ohm if RT equal to 500. So that means V out over RT. So we know that the RT equal to 500 here. So we can straight away use all this formula, right? You can use this formula. Okay. And you also can ignore this one. And then it become delta R, okay, delta R over 4, right, being. And then you want to find the delta V over with the RT, so you can calculate this one, right? Delta R over R, sensitivity, you calculate this one, right? Okay. The last one is about the bridge circuit when we have the analog, the alternate current. So this one we not covered for in this syllabus. Okay, so before that, so let I stretch out this one. So the Western bridge, on what you want to learn about it is delta V over V in equal to delta R over 4. If you look into this, so 4 is fixed and R value is fixed also, and V in also fixed. So the changes will be in term of delta R here, and then the output will be in term the offset delta V, right? So the sensitivity will be delta V over delta R. This we call it the sensitivity. All right. You know what it means? Everything good? Get it? Okay, good. That's what we call it the sensitivity. All right, so that's it for two topics for today. Is it enough, right? Okay. Enough. Right. The same question from me. Do you want to have the class on this Thursday? Can no. Wow, so many guys. Okay, no. Right. All right, so there is no class for this Thursday, so try to spend out to your project, and I know you're quite busy with the test. Okay. And wow, we don't have class on 1. Okay. And I believe 1 May is holiday, right? Wow, we don't have class. I will see you on maybe on 5 May, maybe. Okay. All right. For Muslim, so I wish you Selamat Hari Raya, right? And please be careful, guys. All right. Please follow the SOP, right? Standard of procedure. All right. If not, you will be infected by the COVID-19. Okay. Please be careful. I know that this year we can go for Hari Raya. We can meet our friend. We can meet our girlfriend or boyfriend, right? And blah blah blah. Okay, but be careful, guys. And I wish you Selamat Hari Raya. And for those who don't have anything to do, please look at your project. Okay. Please to find out which component that you can use. Please play around with the Tinkercad. And if you have any question, please let me know. All right. I think that's it for today class. I will see you again maybe on 5 May. Okay. Because 1 is holiday, right? Hari the Labor Day, right? Okay. All right. Thank you, Tai Yon Wen. Selamat Hari Raya too. Right. Don't forget to play the firework, right? So I think you got balloon, right? Tai Yon Wen. Okay. For your Hari Raya. All right. Thank you very much. See you again. All right. Bye bye. Assalamualaikum. And I wish you good luck for your test. Okay. For this subject. Right.
Thank you, Doctor.
Right.
Thank you, Doctor.